Hello everyone, welcome back. Let's talk about another medium problem on LeetCode today. The kth lexicographical string of all happy strings of length n, LeetCode 1415. If you are new to the channel, consider subscribing. I try to make daily videos on the problems related to data structures and algorithm, including detailed explanations, optimized solutions, and step-by-step walkthroughs to help you improve your coding skills. Now to the problem. In this problem, we are given two integers n and k, and our task is to return the kth happy string of all the happy strings of length n sorted in lexicographical order. A happy string only contains the characters a, b and c, and no two consecutive characters in the string can be same. Then in example 1, for n equal to 1, we can have three happy strings of size 1 which are a, b and c, and they are sorted in lexicographical order as well. So when we say k equal to 3, we have to return the kth or third happy string which will be c. So that will be our answer. Then in example 2, n is equal to 1 and k is equal to 4, but we only have three happy strings of length n equal to 1, which is less than k equal to 4. So we will return the empty string as our answer. And finally in example 3, for n equal to 3, we have 12 different happy strings of length 3 which are following, and we have to return ninth happy string which will be this one. So we will return CAB as our answer. And now in terms of constraints, n at maximum can be equal to 10 and k at maximum can be equal to 100. Now in terms of solution, the happy strings only require two validations. One, that only allowed characters are a, b and c, and two, there shouldn't be any two consecutive characters that are same. So one way can be that we generate all possible strings using the characters a, b and c and adhere to both the rules. And this is where backtracking can help us, because with backtracking we can explore all possible character combinations while building each string step by step, and at each step we ensure that the string build conforms to the happy string rules. So we start with the empty string, and then at each step we have three possibilities. Either we can choose a or b or c. Now we conform to rule 1 as we are using only the characters a, b and c, and we conform to rule number 2 as well, as here the string was empty, so all the three characters a, b and c were allowed. And notice that here we have formed the happy strings of length 1, but for us n is equal to 3 and k is equal to 4. We continue with our recursion, and now at this point, since our last character is a, we cannot choose it again. Otherwise, the string will have two consecutive a's and break the rule too. So we choose b and c and get the strings ab and ac. And similarly for this path as well, we cannot choose b but a and c. So we will get the strings ba and bc. And here we cannot choose c again. So we will get ca, cb. And note that now we have got all the strings of length 2. And again at this point, since our last character is b, we cannot choose b again. So we can only choose a and c. So our string becomes aba, abc. And note that this is the point where we have got our base case. That is, we have reached the length of n equal to 3. So we will add these strings to our answer list. So we will add aba to the answer list and stop the recursion tree here and go to the next path and add abc to the result list, as we have reached n equal to 3 in this path as well. Similarly, for this path, as the last character was c, we cannot take c, but we can take a and b and get the strings aca and add it to the answer list, and get the string acb and add it to the answer list. And this is how we will continue with our recursion until all possible combinations of happy strings are explored and added to the answer list. And then we will check the value of k. If k is within the bound of our answer list, then we will return the answer from the kth index. For example, here k was equal to 4. So we will return ACB as our answer. But if the k is out of bound of our answer list, then in that case, we will return the empty string. And this is the more elegant diagram of the same recursion tree. In case you are interested, it is available in the post linked in the description below. And now in terms of time complexity, it will be O of 2 to the power of n, because at each point, barring the first level where we had 3 nodes, all the other levels have only 2 choices where we can choose either of the 2 characters, making the time complexity 2 to the power of n. And in terms of space complexity, it will be O of n if we consider the recursion space. But we are also storing these answers in the result list, which is again equivalent to number of nodes in the last level of the tree, which is roughly 2 to the power of n. Hence, the space complexity is also O of 2 to the power of n. Now let's jump into the code part. First, let's initialize a result list to store all the valid happy strings. Now let's begin the backtracking process to generate all the valid happy strings. For that, we will pass in n to check if we have generated the happy string of size n in the base case. And then we pass the empty mutable string to construct each happy string and the answer list we just created. And once the backtracking is done, we will get the answer list. So if k is within the bounds of answer list, then we will return the kth happy string. Otherwise, we will return an empty string. Now let's write our backtracking logic. First, let's write the base case. If the current string's length is equal to n, that means we have found a valid happy string and hence we will add it to the answer list and terminate the current recursion branch by returning from here. Otherwise, we will continue with our recursive branching. So we will go through all the characters A, B and C in this sorted order and check if the previous character doesn't exist, that is the length of the string is empty, or if it exists then it is not equal to current character, then we will append the current character to the current happy string so that we don't have two consecutive identical characters, and recursively call the backtracking function to continue building the string with this newly appended character and backtrack by removing the current character to explore other possibilities. And now we are done. So let's submit this code. Awesome. And now the question is, can we do better? And the answer is yes. With some mathematics and visualization, we can bring the time complexity down to O of n. However, since this video has already run a bit long, I'll save that explanation for a follow-up video. Stay tuned for that. So that's all for this video. I hope this video was useful to you. If it was, please give it a thumbs up and share it with others who might benefit from it. If you haven't subscribed the channel yet, make sure to hit the subscribe button and turn on the notification bell so that you never miss an update. Your support helps me create more content like this. If you have any questions or suggestions, feel free to leave them in the comments below. Thanks for watching and see you in the next one.